A viewer has pointed out that I have made a rather stupid mistake in a part of the lecture in this series, the lecture number 2D, and since that particular part of the calculation is used later on, that naturally throws some doubt as to the validity of the calculation that is being done here. Let me first explain to you what the mistake that I made was. Then I will show you the correct way of doing it, although frankly, if you're paying attention, you should be able to do it yourself. And finally, I will also try to explain why this mistake does not really affect the final conclusions in that particular lecture. That actually happens to be rather fortunate. Somehow I've made two mistakes and they cancel each other out. But first, let me explain what the mistake was. As you can see, what we did in that lecture was work with this kind of an expression, U inverse lambda A, U lambda bar A bar, U lambda A. And then we substituted for lambda bar A bar an infinitesimal transformation. Later on, we even substituted for lambda A another infinitesimal transformation. And at the end of the calculation, we would end up with rather useful results. In this particular lecture, what I did was substitute U lambda bar A bar by an infinitesimal transformation and use that to figure out how Poincare generators transform under Poincare transformations. So what was the mistake? The mistake was a rather simple and trivial one. If you calculate this out, U inverse lambda A is U lambda inverse minus lambda inverse A. That part is perfectly right. And here we have combined the two Poincare transformations according to the standard rule of combining Poincare transformations, where the Lorentz transformation parts just multiply and the translation does add, but before you add, the original translation, the first one, has to be acted upon by the second Lorentz transformation to form lambda bar A, then add the second translation A bar. That's the standard Poincare transformation rule. Now, when we combine these two Poincare transformations together, you should do exactly the same thing. That is, lambda inverse should act on this translation, and then you have to add this particular translation minus lambda inverse A. And when I did that, I made this stupid mistake that I forgot the bracket here. Lambda inverse should act on the whole translation, lambda bar A plus A bar, not just on lambda bar A. So basically, my mistake was this. This lambda inverse should be acting on not only lambda bar minus identity A, which part is perfectly alright, but it should also be acting on A bar. So instead of just A bar, which we had in the original video, we should really have lambda inverse A bar sitting here. And that looks like a big problem, because we are going to use this very thing to talk about the Poincare transformation properties of the Poincare generators. Let me just continue a bit and show you what we did there. We replaced U lambda bar A bar by an infinitesimal transformation, plugged it in here, and just use this result, except that instead of lambda bar I used identity plus omega, and instead of A bar I used epsilon. But again, the mistake continued. This should be lambda inverse omega A plus epsilon, not lambda inverse omega A plus epsilon. Now the next step, of course, was to replace U identity plus omega comma epsilon by its expansion in terms of the Poincare generators, which is rather standard. So we did that. We did the same thing on the other side. Remember, this is just an infinitesimal Poincare transformation with identity plus lambda inverse omega lambda as a Lorentz transformation. So this is the infinitesimal part. And you also have an infinitesimal translation. This is infinitesimal because omega here is infinitesimal, so is epsilon. And therefore, we did the same thing on the right hand side. Once again, my mistake continues. This really should be omega A plus epsilon rho. And then I took some time to explain how to expand out lambda inverse omega lambda's rho sigma element in terms of the Lorentz transformation matrices and so on. So it looks like the error has continued. In fact, it has. And what saves the day for us is this. Lambda inverse omega A plus epsilon's rhoth component. We worked it out and we showed it is lambda omega rho, omega mu nu a nu. I'm not explaining that again here because that's already there in the original video. But the important point is I somehow managed to get back the bracket here. This is really lambda mu rho epsilon mu. If this really had been what I was looking at, I should have ended up with lambda mu rho, omega mu nu, a nu, plus epsilon rho. This is what I should have had if this were really what I was looking at. But because we are really looking at this, what I really get is this quantity. That is the second term here, which is just lambda inverse epsilon's rhoth component. That really has this form lambda mu rho epsilon mu. Just to show you how that works, this is the upper rhoth element of this. Now the lower rhoth is simply going to be epsilon mu lambda mu rho, and then we lower and raise this index simultaneously, that we can always do, and also lower the rho index on both sides, and that gives us lambda mu rho epsilon mu, exactly what we have written here. And this is what we have used in the subsequent part of the calculation. So the rest of the calculation is perfectly alright. Since this could be a bit confusing to people who are seeing this for the first time, and I really don't want you confused, I decided to make this errata video to explain this part to all of you. I hope that this really helps.